Hello everyone. Today we're going to be solving quadratic equations by graphing. So to start, an equation is a mathematical statement which shows equality between two expressions. We have four different equations here. Two of the equations from above are shown below. Algebraically solve the two equations using your equation solving skills learned in Math 10C. So the goal with algebraic equations is to get x, or the variable, on its own and in the numerator or upstairs. So with this first equation, I want to get x on its own, so it would be helpful to get rid of the 9 from the left side. If I do that, I end up with 2x. Let me try that again. I end up with 2x equals 16. Now I want to get rid of the 2 from the left-hand side, so I need to divide both sides by 2. And now I have x equals 16 divided by 2, which is 8. With the one on the right here, it would be helpful to expand this first. And same thing with this. Hopefully we can simplify it a little bit and then get x on its own. So let's start by doing the left side. 5 times x is 5x. 5 times negative 3 is negative 15. So we have 2x on the right. 7 times x is 7x. And 7 times negative 5 is negative 35. Now I can group these two together. So 2x plus 7x is 9x minus 35. And then on the left I have 5x minus 15. Okay, I think I might bring all the x's to the left side, so I'll need to get rid of this number. So add 15 to both sides, giving me 5x equals 9x, and negative 35 plus 15 is negative 20. Now I need to bring the 9x over to the left side, so I need to subtract 9x from both sides. That gives me now on the left negative 4x, and on the right I have negative 20. Now, I'm pretty close. I just need to get rid of the negative 4 on the left side. In order to do that, I need to divide both sides by negative 4. So negative 4 divided by negative 4 is positive 1. So I have 1x equals negative 20 divided by negative 4, which is 5. Okay, and if we want to confirm that, starting with the first equation, 2 times something minus 9 needs to be 7. So I should confirm that the left side is consistent with the right side. So if I put in my solution, which I found to be 8 in there, the left side of this equation should give me 7. So 2 times 8 is 16. 16 minus 9, we need to confirm that's equal to 7, and 16 minus 9 is indeed 7, so that solution works. Okay, with the other one, I need to check that when I put a 5 in for x into the original equation, that works out so that the left side is equal to the right side. So here, plus 7 something minus 5. So when I put my solution of 5 in for x, so everywhere I see an x, I put a 5. So we need to confirm that the left side equals the right side. We do BEDMAS on the left. 5 minus 3 is 2. 5 times 2 is 10. Okay, and then simplify the right side. So 2 times 5 is 10 plus 7. 5 minus 5 is 0, so 7 times 0, we have 10. 10 indeed equals 10, so that is a good solution. So, the equations you solved above are linear equations. The other two equations that we didn't do are quadratic equations. During the next few days, you will learn how to solve quadratic equations algebraically. But for now we will solve them graphically, which is a little bit simpler. So, next page, how can the graph below how can the graph below be used, oh that's weird, be used to solve the quadratic equation 2x squared plus 5x equals 12. So to start, notice 12 is a horizontal line at y equals 12. So if we put in our graphing calculators y1 equals 12, that would give us a horizontal line. If I were to do the left side of this equation, so if I were to put that in for y2, I would get a parabola that matches the one in the picture here. So it would look like that. Now, the points of intersection turn out to be the solutions to this. So we have an intersection point, maybe 1.5, 12, and we have another intersection point here, negative 4, 12. So it turns out these x values at the intersection points are the solutions, and you can try that out. So maybe try, so starting with this, we need to confirm that the left side equals the right side. For example, if I put in x equals 1.5. So if I do 2 times something squared plus 5 times something, I need to check that that equals 12. So my solution here, I am supposing, is 1.5. So again, just using that x value. So 2 times 1.5 squared is 4.5, and 5 times 1.5 is 7.5, and we need to check that that equals 12, and 4.5 plus 7.5 turns out to be 12. So that's a good solution. Okay, and you can check that as well for the other intersection points. So 2 something squared plus 5 something, check that equals 12. The other possibility is negative 4, so maybe try that on your own. Okay, here's another one. How can the graph below be used to solve the quadratic equation 2 bracket x minus 3 bracket x plus 4 bracket? So in this case, we don't have a horizontal line, sort of obvious as the other question, but it's sort of been shifted so that the horizontal line is the x-axis. And if we were to graph this for y1, so 2x minus 3x plus 4, we would get this parabola. Okay, and these sort of intersection points, I guess, if you like, because the horizontal line here represented is the x-axis. These intersection points, so we have negative 4, 0, and we have 3, 0. Turns out that these are the solutions to this equation above. So notice if I put negative 4 in here, that whole thing goes to 0, and if this is 0, then this whole thing goes to 0. And similarly, if I put a positive 3 in for x there, that makes this thing 0, and it doesn't matter what this other thing is, 3, so it would be 3 plus 4, 7. So we would basically have 2 times 0 times 7, which is also all 0. So if either x equals negative 4 or x equals 3, that makes the whole left side of this equation 0, and that would be considered to be a solution. Okay, let's look at solving another quadratic equation graphically using the concepts from above. So the first method, what we do is we graph two functions and find the points of intersection. So we put y1 is the left-hand side of the equation, and we put y2 equals the right-hand side of the equation. We don't need to simplify, we don't need to, so as long as it's all in terms of x, we just put the left-hand side in for y1 and the right-hand side in for y2 and find the points of intersection. So typically this is the least amount of work required. amount of work. So this is the quick way if it's available. And in order to find the intersection points, what we do once we graph the equation in our graphing calculator, we hit second and then trace, and then go down to number 5, which is the intersection. So to solve the equation x squared minus 4x plus 1 equals x plus 1, we need to determine all the values of x that would make the statement true. In other words, all the values of x that make the left side of the equation equal to the right side. The x values can be found graphically by first graphing y equals the left side of the equation, and also graphing y equals the right side of the equation. So the graphs of y equals x squared minus 4x plus 1 and y equals x plus 1 are shown below. Label them. So we have a linear one here. That should probably be this one. Right? So we have y equals x plus 1. And the parabola here would be represented by this equation. So that would be y equals x squared minus 4x plus 1. Now we are asked to circle the points on the graph where the two functions are equal to one another. They would be there and there. So if you think of each of these functions as sort of a machine, so we have a function of x, we have an input and an output. So when I put x equals 0 into this machine, this function machine, if you like, spits out a value of 1. And similarly with this other sort of function machine, when I feed in a value of x equals 0, the function spits out a value of 1 as well. So that's consistent with the other machine. And if I were to feed in a value of x equals 5, so x equals 5, this function spits out a value of 6. And with the other function machine, if I put a value of x equals 5, feed it in, it also feeds out a y value of y equals 6. So that's consistent with this one over here. So the x values that will satisfy the equation are x equals 0 and x equals 5. So algebraically verify both of the answers by substituting them back into the equation. So the equation originally was x squared minus 4 times x plus 1 equals x plus 1. So it should be true that when x equals 0, so everywhere I see an x, I put a 0. We should have the left side equal the right side, so we need to just sort of independently figure out what the left side is. So 0 squared is 0, minus 4 times 0 is 0, plus 1, that's just 1. Okay, and then the right side is 0 plus 1, which is 1, so 1 equals 1. That's great. The other solution, x equals 5. So everywhere I see an x in the original equation, I will put a 5. So it should be true that the left side equals the right side independently. So if I put a 5 in everywhere I see an x, I get a good result. So 5 squared is 25, minus 4 times 5 is 20, plus 1. Okay, 25 minus 20 is 5, and then plus 1 is 6. So it should turn out that the right side is 6, and 5 plus 1 is indeed 6, so that is also a good solution. Great. so first method, summary. What we do is we graph y1 equals the left side, so y1 equals left-hand side of the equation, and y2 equals the right-hand side of the equation. The x-coordinates of the points of intersection will be the solutions. Okay, second method, a little bit more work required, but we ultimately just graph it at the end and we're off. So what we do is we rewrite the equation so that one side is equal to 0, and then we just find the x-intercepts. So this time we're not finding the intersection points, we are finding the x-intercepts. You could sort of think of that as the horizontal line is now moved to the x-axis, so it's y equals 0. So we're finding the intersection points of whatever parabola we get with the x-axis. So that is the x-intercepts, or the zeros. So to solve the same equation, x squared minus 4x plus 1 equals x plus 1, we still need to determine all the values of x that would make the statement true. However, when using this method, we rearrange the equation such that one side is equal to 0. And so if we do that, starting with the original, it looks like most of the stuff is on the left already, so might as well just bring everything to the left side. So that would give me x squared minus 5x plus 1 equals 1. And then we just bring the 1 over as well. And we have x squared minus 5x equals 0. So then in this method, we'll put that in for y1. And if you like, y2 equals 0. But that's just the x-axis. So the equation, when rearranged, will be x squared minus 5x equals 0. Okay, the graph of x squared minus 5x is shown. Label it, so here we have y equals x squared minus 5x. Since we're now trying to find the solutions for x squared minus 5x equals 0, we need to look where the graph of x squared minus 5x has a y value that is equal to 0. So sort of we're finding the intersection points with the parabola and the x-axis. So the important points to look out for here are there and there. This time we're finding the zeros. Okay, so state the values of x that will satisfy the equation. The x value here is 0, and the x value here is 5. So x equals 0 and x equals 5, which we can algebraically verify. So starting with our equation that was modified, we need to confirm that. So when I put x equals 0 here, 0 squared is 0, minus 5 times 0, also 0. 0 equals 0, true. Alright, let's do it again for x equals 5. So we would have, okay, squared minus 5. So everywhere I see an x, I put a 5. So 5, that was the other solution. 5 squared is 25, minus 5 times 5, also 25. Does that equal 0? Well, yeah, 25 minus 25 is 0. So that is another good solution. So, summary for the second method. What we do is we rewrite the equation so that one side of the equation is equal to 0. Then we graph the non-zero side of the equation. And in this case, the x-intercepts of the graph are the solutions to the equation. Remember, both methods will give the same solutions since both methods solve the same equation. So you should get a consistent result when using either method. Okay, what is the maximum number of solutions for the equation 2x squared minus 4x minus 1 equals negative 2x plus 3? It's going to be 2. So we have a parabola and a linear equation. At most, if we have a parabola and a linear equation, the most number of intersection points is going to be 2. Alright, solve graphically using both methods and your graphing calculator. So first method, we put two graphs, so I put that for y1 and I put that for y2. So I have y1 equals 2x squared minus 4x minus 1. And I have y2 equals negative 2x plus 3. So when I put this into my graph, I get a parabola. So that's your 2x squared minus 4x minus 1. And I also get a linear graph. Okay, and what we do is we just find both points of intersection. So we do that one and that one. So the intersection point here on the left is negative 1, 5. And on the right is 2, negative 1. And the solutions to the graph, or to this equation, are x equals negative 1 and x equals 2. So real quick what that looks like on your graphing calculator, you go y equals, type your two equations in, so that's the left side, that's the right side, you hit graph, there's the parabola, there's the linear equation. We go second, trace, go down to number 5, intersect, and you need to pick the two graphs, and generally a good idea to pick 2 points on each graph in the neighborhood of the intersection point that you're interested in. So I select the parabola and the linear graph in that area, and I tell it to guess. So I hit enter again, and there's the intersection point. Now to find the second intersection, I do second trace again, intersect, and I'm going to pick 2 points on each graph in the neighborhood of the second intersection point, and that's the second intersection there. Now, for the second method, we need to rewrite the equation and then just do one graph. So starting with 2x squared minus 4x minus 1 equals negative 2x plus 3. I need to bring everything to one side. So since most of it is already on the left side, let's bring everything to the left. So add 2x to both sides. That gives me 2x squared. Negative 4x plus 2x is negative 2x, and I have negative 1. So that's gone from the right side, and I have 3 remaining. Then I need to subtract 3 from both sides. So now we have 2x squared minus 2x minus 4 on the left, and 0 on the right, and now we're set. So what we do now is we put y1 equals 2x squared minus 2x minus 4, and connecting it to the other method, I guess you could put y2 equals 0 and then find the intersection points again. That's not necessary though, because what we're going to do in this case is just find the zeros. So we graph that. We have the first intercept, x-intercept is negative 1, 0, and the second intercept here is at 2, 0. So our two solutions are consistent with the one we did over here. So negative 1, okay, negative 1 as well, and 2, and we got 2 as well. So real quick what that looks like on your graphing calculator, you go y1 equals whatever you found. y2 you could put 0 if you want, I won't do that now. There's our parabola. We go second trace. We need to find the zeros in this case. I pick a point to the left of the first intercept that I want to find, and a right. Tell it to guess, negative 1, 0. And to find the other intercept, I go 0, pick a point to the left of the point I'm interested in, and pick a point to the right, tell it to guess. There we go, that's the other intersect. Okay, next example. The surface area of a cylinder can be determined using 2 pi r squared plus 2 pi r h, where r is the radius of the base and h is the height of the cylinder. Suppose the height of a particular cylinder is 12 centimeters. Write a formula for the surface area in terms of the radius. So surface area in terms of the radius. So we have here the height of the cylinder is pinned down, that's 12 centimeters. And we have surface area dependent on the radius, so surface area as a function of the radius, we would write 2 pi r squared plus, and then if we put 12 in there, I can sort of do 2 times 12, and then I'll have 24 pi r. So 24 pi r. And that is the surface area as a function of the radius. So next, determine the radius the base must have for the cylinder's surface area to be 175 centimeters squared. State your answer to the nearest hundredth of a centimeter. So what we know is the surface area needs to be 175. And that needs to be the left side of this equation. So we go 175 equals 2 pi r squared plus 24 pi r. Now, if we could solve this algebraically at this point, we basically just need to figure out what r is algebraically, but for now we're just doing graphically. Okay, we can do either method. We can let that equal y1 and that equal y2, making sure that we substitute x's in for r's because our graphing calculator doesn't really tolerate that. Or we can get everything equal to 0, so maybe bring everything to one side and let the equation be 0. So we have 2 pi times x squared plus 24 pi x minus 175. So if you put that in for y1, and now we just find the x-intercepts. Graph that, so y1 equals that equation there would be, so that's minus 175 that's missing. And you'll notice if you graph it, it probably doesn't show up entirely. So if you adjust your window settings, so your window settings, window is next to y1, or sorry, window is next to y equals, so you just do y equals, and you would just type all those values that I have there, 10, okay, this is negative 500, and y max is 200, and if you don't want the ticks on the y-axis to be so close, you can just change the y-scale to 50, so that just zooms it to an area that's suitable for this question. And then so we do 2 pi x squared plus 24x, so 24 pi x minus 175. We hit graph. That's what it looks like. And we find the x-intercept. So we go second trace, find 1, 0. So I need to go, let's pick this one over here, pick a point to the left, pick a point to the right, tell it to guess. There we go, negative 13.99. However, that's giving us a sort of non-real cylinder. So we have the radius is equal to negative 14 roughly. That's not a adequate solution because we have a negative radius, which makes no sense. So what we do is we pick the other intercept. So this is actually a physical solution over here. Pick a point to the left, pick a point to the right, and there we go, 1.99. So it turns out that the left intercept is a non-physical solution. Having a negative radius doesn't make sense in this context. So that would be sort of an extraneous root. So we graph that. There we go. So the radius we should use is that one. So radius equals 1.99 centimeters. Because this one we have radius is a negative radius doesn't make sense for a cylinder. It might be some kind of hypercylinder. Okay, we can check that. So let's see, surface area equals something. If I sub 1.99 in for R, so everywhere I see an R, I'm going to put a 1.99. So I go 1.99 there, 1.99 there. Okay, and this first one gives us 24.88. Second one, 150.04. That gives us 174.9, which is good to a close approximation. So there was a bit of rounding there involved, so we got pretty close to our desired result, which was 175. Okay, your assignment for today, textbook questions there. See you next time.